A massive object named 3I Atlas is rushing toward our sun right now, and astronomers around the world are on high alert. Atlas moves, shines, and acts like no visitor from the stars we've ever seen before. It's an enigma. Its path is precise. It's chemically bizarre, and its presence is forcing scientists, for the third time in history, to rethink everything about the way interstellar objects behave. Is Atlas just the latest cosmic interstellar rock? Or does it tell us something new, maybe even something extraordinary about the universe around us? Interstellar visitors are rare. Let's start with why. For most of human history, our telescopes weren't sensitive enough to notice the difference between local comets and those sent flying from distant star systems. These are true wanderers, forged in alien environments, swept along by gravity, bumps, and twists that take them far from home. In fact, only twice before have scientists ever tracked and confirmed such an object. Oumuamua in 2017, with its odd shape and rapid tumble, and Borisov in 2019, a classic icy comet streaking through at high speed. Both ignited global debates and triggered countless new studies. But Atlas, first spotted on July 1, 2025, breaks away from the comparisons. Its initial observations didn't just puzzle astronomers, they set off alarms. It bends the rules. Atlas's behavior is so strange, so packed with contradictions and mystery, that some scientists quietly admit they've never seen anything like it. From the very start, Atlas is an anomaly. What do we mean when we say anomaly? For scientists, anomalies are opportunities, signs that some hidden rule or process is waiting to be discovered. Sometimes the anomaly points to an error or misunderstanding, but sometimes, just sometimes, it marks the beginning of a new era in knowledge. The universe doesn't let go of its secrets easily. Let's dive right into the oddities, the snowball of mysteries that have made Atlas the focus of the most intense astronomical campaign in years. First, trajectory. Atlas slices into our solar system with jaw-dropping precision. Most interstellar objects, by their very definition, should rush in from a scatter of angles, steep and unpredictable, like marbles tossed on a spinning plate. Yet, Atlas rides perfectly along the solar system's ecliptic plane, tilted just 5 degrees off the exact course our planets travel. Experts liken it to a cosmic bullseye, a 1,000,000-to-1 shot. You could throw tens of millions of similar objects from outside the solar system and almost never see one come so close to matching the planetary path. Can you picture it? Imagine the solar system as a busy highway. There are thousands of lanes, streams of motion in every direction. Most wandering travelers cut across abruptly and never stick to the traffic patterns. But here comes Atlas, not just moving against the flow, but staying almost perfectly in its lane. Retrograde 2, meaning it's swimming upstream while remaining eerily flat. Probability models, the ones designed to make sense of random arrivals, show this scenario almost never happens. Is this just luck at the galactic scale, or does it hint at a deeper principle, one we haven't yet uncovered, about how cosmic objects find their way across the stars? Second, the ghostly mass. When Atlas first appeared, astronomers measured its brightness to estimate mass. The numbers were huge, 33 billion tons. That's not just another hunk of rock. It's a bulk so massive, so energetic, that Atlas should have tugged on everything it passed. Most famously, when it approached Mars in early October, observers worldwide expected some sort of gravitational signal, a momentary wobble in the Martian orbit or a tiny nudge in the course of spacecraft circling the planet. But every sensor came back blank. Zero effect. This is more than a mathematical quirk. Atlas's weight should have left fingerprints everywhere. Instead, it's as if Atlas is hollow, built from some cosmic foam, a shell with enormous volume and almost no substance. It shimmers in sunlight with the signature of a heavyweight, but acts like a ghost, massive in appearance, feathery in consequence. Some researchers imagine a structure so porous, so delicately webbed, that it floats above the gravitational game. Have you ever held something that looks massive but feels incredibly light? What was your first reaction? That's the question stumping the best and brightest astronomers now. Third, the rebellious jet. Normal comets, the icy leftovers of planet formation, all share a single trait. Their tails stream away from the sun, sculpted by the solar wind, a constant gale of charged particles and radiant energy. It's nature's rulebook, followed for billions of years. Atlas, instead, shoots a powerful jet of gas directly at the sun, defying the wind and tradition. It's like piloting a boat into the teeth of a hurricane, somehow cutting forward instead of being driven back. What's powering this jet? Spectroscopy reveals the gas is dominated by carbon dioxide, with a ratio to water vapor 8 times higher than anything in the comet family archive. Most comets are loaded with water, a sign of their cold, primordial birthplaces, not Atlas. Its composition is strange, perhaps the result of formation at extraordinary temperatures, in uniquely irradiated environments, or maybe driven by mechanisms not yet defined in planetary science. Physically, Atlas's surface is covered with densely packed fine dust, not the loose, fluffy grains seen on regular comets. This might help explain its strange jet. The way sunlight strikes, disperses, or even gets trapped in compact grains could focus energy, powering sunward outflows. So, to recap, precision orbit, mysterious ghostly mass, and a tail that refuses to follow the rules. Any one would be enough to catch scientific attention, but Atlas, rare among the rare, stacks these anomalies together. Which one do you find most unbelievable? Do you find Atlas's flight path, mass, or the trail it leaves behind more fascinating? With Atlas's passage inward, the global science community lit up. The Atlas survey in Chile, where the object was originally spotted, was soon joined by telescopes in Hawaii, Arizona, Europe, and Asia. Data swarmed in, measurements of light, heat, chemical fingerprints, and dust patterns. Space agencies coordinated orbital instrument campaigns, hoping to catch even the tiniest hint of interaction with planets or probes. Ever wondered how astronomers weigh a comet without touching it? They watch its light, track its motion, and see how it moves other objects nearby. Like checking if a passing truck rattles the windows on a busy street. Atlas shot by, and not a single rattle in the data. Across continents, astronomy teams compare notes, squabble over interpretations, and trade ideas in late-night calls. Atlas is a game-changer. For some, it's the perfect example of cosmic diversity. For others, it's a puzzle that calls for new rules. Meanwhile, science communicators and journalists rush to translate the discoveries for the public. Social media floods with diagrams and hypotheses. YouTubers make their own animations. Kids in classrooms ask questions about the giant visitor that messed up Mars. The search for meaning spills out from research labs into tweets, comment threads, and open debates. What could its arrival mean for our understanding of the universe? The climax of the Atlas enigma is approaching, and yet, at the most critical moment, humanity will be blind. This is the great observational crisis. From mid-October through early November, the geometric alignment of Earth, the Sun, and Three-Eye Atlas is such that the object effectively vanishes. We enter the window of superior conjunction. This is not an accident of fate. It is a direct consequence of the object's flat, 5-degree trajectory leading it directly into the Sun's glare. The observational blackout officially stretches from October 22nd to November 7th. During this 16-day period, the crucial moment of maximum velocity and closest approach to the Sun, the precise window for a natural breakup or, critically, an intentional Oberth maneuver will occur unobserved. The limits of our technology are dictated by safety. Ground-based telescopes and our most sensitive space assets, like the Hubble and James Webb Space Telescopes, are programmed with strict solar avoidance protocols. They cannot point within 30 to 85 degrees of the Sun for fear of frying their delicate optics and instruments. This is why we have no hope of capturing direct imagery or spectroscopic data of Atlas as it whips through perihelion. This technological limitation has already compounded the mystery. Recall the high-rise imagery from the Mars Reconnaissance Orbiter, the only potential source of close-range data before the blackout. Those raw frames, taken at 50,000 times fainter than the camera's design limit, were initially flagged as noise by the ESA team. Crucial, ambiguous pixels that could reveal the structure of the sunward jet or the hollowness of the shell are currently trapped in processing pipelines. By the time that data is successfully calibrated and released, potentially in late November, the event will be long over. This blackout means that any sudden, dramatic change, be it a massive, natural fragmentation due to thermal stress, or a calculated 20 km/s deceleration burn will occur covertly. When Atlas finally re-emerges near the pre-dawn horizon, astronomers will not be watching the event. They will be searching for the smoking gun in the trajectory residuals, piecing together a forensic analysis of what transpired during the unobserved cosmic moment. The critical test for the true nature of 3I Atlas is being performed now, and we can only wait for the final results to be radioed home. Now, let's shift the conversation toward interstellar object detection. For centuries, all comets looked alike, drifting through the night sky. It was only recently, thanks to improved telescopes and sharper algorithms, that interstellar visitors could be separated from the local crowd. Oumuamua, the first spotted only after it zipped past Earth, was gone before astronomers could analyze it in depth. Borisov, the second, gave scientists more time. Its icy nature, active jets, and regular shape made it easier to study. Atlas is the third, but its presence in our skies is anything but ordinary. Spotting Atlas meant threading a cosmic needle. The Atlas survey's powerful cameras swept thousands of images every night. Among the routine stream, one light moved too fast and too straight to be anything known. Computers flagged the object, checks followed, and confirmations spread soon. Atlas became a global sensation. How many other interstellar visitors might slip by unnoticed, mixing with local comets or asteroids? Some astronomers estimate dozens each year, perhaps even more, masked by similar speeds or unlikely arrival angles. A few optimists argue for hundreds, floating invisibly across the solar system. The hunt has just begun. With Atlas on full display, the scientific world doubled down. Coordinated campaigns took turns photographing, analyzing spectra, and listening for outgassing. Space probes watched for any hint of physical force, a tug, a wobble, a shifting dust grain in the nearest planets and satellites. Ground-based teams tracked light curves, looking for tells in the speed or spin of the visitor. Every new readout broke expectation. Atlas confirmed itself as a cosmic contrarian velocity, brightness, composition, and path all playing against established models. Meanwhile, debates raged about what this might mean for the search for life, for cosmic engineering, and even for the story of our solar system itself. Did Atlas form in a regular star system and then get ejected? Was it the product of some process we know, just taken to an extreme? Or was its collection of anomalies the first hint at something made, not born, in deep space? Which outcome do you find more exciting? A natural relic or the first physical evidence of cosmic technology? For now, the safe answer is that all doors remain open. Both tradition and possibility have seats at the table. As Atlas neared its closest approach to the Sun, the dramatic moment known as perihelion, everything in the data got sharper. Brightness peaked, velocities climbed, and spectral lines grew clear. Researchers readied for the story's climax, stacking up findings, sorting surprises, and planning for the biggest reveal. Now comes the bombshell, Atlas's final breathtaking anomaly. Atlas's chemistry, always strange, takes a left turn into the impossible. As it approached the Sun, planetary scientists used massive telescopes, Hubble, Keck, and more, to break down its outgassed material. Then, the numbers came back, and jaws dropped. Atlas was ejecting nickel tetracarbonyl, a compound prized in Earth's advanced manufacturing and metallurgy, but virtually unheard of in deep space bodies. Nickel tetracarbonyl is a complex molecule made up of pure nickel and carbon monoxide. In laboratories, it's used for refining metals and making specialty alloys strong enough for rockets and satellites. But in space, the only time nickel and iron appear together is after supernovae and cosmic mixing. They're born as twins. Yet Atlas spits out nickel in quantities that suggest a different chemistry, a separation never measured before. Why is this so shocking? Because forming nickel tetracarbonyl under natural circumstances requires a blend of elements and a setting that's incredibly rare, or perhaps, conditions close to the artificial. Could Atlas have formed in a cold region, blasted by radiation, or cooked by other cosmic forces? Could an unknown process in interstellar space create compounds we've never thought possible? Some scientists mutter technosignature, a faint possibility that something inside Atlas was engineered, sorted, or built. Others believe in wild natural chemistry, planetary formation at the edge of possibility, a testament to the creative chaos of the universe. If you were the first to find a never-before-seen chemical in space, what would you do? Would you trust your instruments, investigate further, or open the door to more questions than answers? As the chemistry revelations spread, excitement went global. News outlets scrambled, social networks lit up, and science podcasts debated implications live. Academic societies called emergency meetings. Astronomers from rival teams started collaborating, eager to share data, test instruments, and propose new analyses. For a brief moment, Atlas was everywhere. Trending hashtag, viral meme, and headline news. The build-up reached fever pitch. In classrooms and coffee shops, amateur astronomers pitched theories. Artists drew imagined views of Atlas's sunward jet. YouTubers streamed hours of speculation, inviting fans to vote on what the chemistry might mean. The buzz was electric: 1 comet, 3 weeks, a universe of possibilities. Then, just as the story was approaching the peak, the solar system threw up its own cliffhanger. Atlas was about to slip behind the sun, lost from view at the crucial moment. From October 22nd through November 7th, Atlas would pass into Superior Conjunction, hidden behind the blazing disk of the sun, totally unreachable by even our most advanced telescopes and orbital cameras. This wasn't careless planning. It was an unavoidable dance of motion and geometry. Earthly technology, for all its power, could not risk the sun's dangerous glare. Instruments might fry, cameras would be overwhelmed, and data would be corrupted. So, for 2 whole weeks, the cosmic visitor played out its next chapter in absolute secrecy. Astronomers waited, their eyes on the clock, their models ready to leap into action once Atlas would re-emerge. But in those hidden days in that cosmic theater, where unimaginable things might unfold, everything was speculation. The object might fragment, change course, or unleash energy in a process that could answer humanity's deepest questions, or leave only a new set of mysteries behind. What did we expect to find when Atlas returned? Astrometry teams stood ready to measure its velocity, hunting for any sign of a sudden, step-like drop in speed, a crisp change, too large to be caused by ordinary outgassing or solar nudges, would suggest that Atlas had performed a maneuver, a deceleration so sharp it could only point to a major event. If, for instance, Atlas lost 20 kilometers per second in its outbound trajectory, scientists might finally have solid evidence of the fabled Oberth effect in play for a natural, or perhaps engineered, object. The world would watch as numbers and charts tried to tell the story of what happened in darkness. But what if Atlas had shattered? A simple breakup pattern, fragments scattered at random, pushed by radiation pressure, would match a classic comet's demise. Yet, if the debris followed ordered, non-random tracks, perhaps accelerating or veering away under unseen power, researchers would have to reckon with the possibility that Atlas was more than a loose pile of rock and dust. They'd look for clues, organized trails, sharp boundaries, or even small pieces steering themselves as if under control. The chemical profile was another battlefield of ideas. Scientists would repeat their spectral analysis. If the signature of nickel tetracarbonyl, or the high output of carbon dioxide, suddenly vanished at once, far beyond normal model predictions, it might point to a deliberate exhaustion or containment of volatile materials. Or, it might mean Atlas's surface was altered, its internal processes spent, its story changed forever in the glare of the Sunday. This kind of forensic science, piecing together what happened while no one was watching, demands patience, rigor, and creativity. Some teams even partnered with defense agencies, cross-referencing satellite radar and mysterious signals for any coinciding anomalies in Earth's upper atmosphere. If fragmented pieces rained down, or if strange echoes sparkled across the globe's sensor networks during Atlas's closest approach, it could hint at an external trace left behind. For students, educators, and science fans, the blackout became a teaching moment. Why do we lose track of such treasures at the moment of greatest suspense? What risks and safety limits must always govern our most expensive, most delicate telescopes? Stories circulated about past conjunctions, about the engineering trade-offs that save multi-billion-dollar instruments from catastrophic failure, even as they cost us answers in the heat of discovery. You might wonder, how did researchers feel during this waiting game? Some describe sleepless nights, running computer models and theorizing about what could happen next. Some worried the hype might lead to disappointment. Others hoped for a surprise, a twist in the data that would validate months, even years, of speculation. The scientific spirit thrives on both hope and caution. Let's pause for a thought experiment. If you could choose just one type of data to receive about Atlas after it re-emerged, what would you pick? The exact change in velocity? A microscopic breakdown of surface chemistry? Detailed images of any debris field? Every choice, every answer, helps shape the future of our cosmic investigation. Keep watching the sky, stay curious, and be ready for whatever the universe throws at us next, because if Atlas taught us anything, it's that the cosmos is deep, mysterious, and always worth exploring.